Okay, great. Good morning. Any questions, Jessica, Oksana, Sandra, any questions you want to start off with today? No? Okay. All right, so we have really one more topic to discuss in chapter 10, which is the kinetic molecular theory of gases. So we'll talk about that today. And then the next topic coming up is chapter 6, which I find exciting. That's an exciting chapter. So we'll talk about that when we get to it. So let's talk about the kinetic molecular theory of gases. So far in the discussion of gases, we talked about the variables, the pressure, the volume, the number of moles, and the temperature. And what we did was we took those variables and we turned them into, the lights there might be a little bit hard for you to see. We turned them into certain what we call gas laws. And of course we had a bunch of them, right? There was pressure volume, there was volume temperature, there was volume moles, and then there was the ideal gas law. And then we said, hey, you can even take the ideal gas law and kind of turn it into a density equation. There we go. And then we did, yesterday, we looked at the gas mixtures, and we said the total pressure was the individual partial pressures, P1 plus P2 plus P3 plus P, however many gases you have. And then we said, hey, there was this other thing you could do, which is you could find the pressure of one of those gases, the partial pressure, if you took the mole fraction of that gas and then multiplied that by the total pressure. So those are all what we call gas laws. And don't worry if you don't remember all of them. Write them all down on like a piece of paper for yourself so that you have them next to you. And I guess one thing in here, a couple of these equations have the gas constant, 0.082057 atmosphere liters per mole Kelvin. So these are very useful little equations that we can use to predict gases, find the pressure, find the volume, find the temperature, all of that. But what we left out in all of this is really what underlies all these gas laws, which is the theory of gases, right? So a law, these are gas laws, a law is really, in the scientific community, it's really just an observation of a pattern that is observed over and over again. So if you see that, for example, people eat more, they gain weight, and you start doing experiments, you say, hey, yeah, when people eat more, they gain weight. You could make a law out of that. You could say that the weight gain is dependent on how much you eat. And we all know that's true. And that's what these gas laws are. They're just sort of relationships that people have observed to occur over and over again. So they call them a law. Okay. And you can have violations of the law. There are cases where the pressure times the volume is not constant. That happens. And so those are the things that we study in the sciences, is when do these laws get broken and what's causing them to be broken and all of that. So what we're going to talk about now is the theory of gases, which is more about the explanation for why gases behave the way they do. Why is it that the pressure of a gas times its volume is constant if the temperature is not changing? Why is it that the molar mass of a gas is dependent on the density of the gas? Those sorts of things, okay? So the theory that we're going to use is the kinetic molecular theory of gases. And this is in section 10.6, and there are several videos that I've made of the example problem, the sample problems, and the practice problems and stuff like that. And there's actually even a separate lecture on YouTube for this for this section, okay? So the KM theory, so we'll call it KM theory just to make it easier to remember. Kinetic molecular. Kinetic, we talked about that when we looked at energy. Kinetic, it has something to do with motion, right? Kinetic means movement. Something's moving. Molecular just means molecules. So really what we're talking about is the motion of molecules. And that's really the underlying theory right there. It's pretty simple. The underlying theory is that molecules, if we're talking about gases, are in motion. They're moving around. They have kinetic motion, kinetic energy. Okay? So really the idea is gases are comprised of large numbers of molecules in motion. And I'm going to put in parentheses that this motion is random, meaning it's not going in one particular direction or another direction. They're bouncing all over the place. Okay. And I'm going to make a couple of other points about them, which is that pressure, what we call pressure, is a result of collisions of these molecules. Every time a molecule collides with something, it exerts a force. As it exerts a force, that creates a pressure, okay? And I'm also going to claim that the molecules don't attract or repel each other, but they collide. They can collide with each other. And it's those collisions that cause pressure. And then there's really one more thing that's important here, and that is that as the temperature of a gas increases, in other words, as the gas gets hotter, the molecules tend to move faster. Okay. Now, when you look at lectures or you read books, you'll find slightly different wordings of this because people just word things differently. But that's essentially the kinetic molecular theory. Large number of molecules. Imagine a mole of molecules, how large that number is. They're colliding with each other. They're in motion. They're moving around randomly. They're not attracting each other. So they're not acting like little magnets. If you take two magnets, they attract each other. Or if you charge up your hair, the hairs will stick up. They're not repelling each other like that. They're just moving around and colliding with each other. Okay. And if they get really, really hot, they're just going to move faster. And if they get cold, they're going to move slower. Okay. And that's the kinetic molecular theory of gases. And essentially what Boltzmann did and other physicists was they said, okay, if that's the case, let's make little mathematical models for them and develop all these equations based on Newtonian, motion and stuff like that, kinetic energy, forces, velocities, and all of that. So people go into that whole field of like figuring out all the mathematics. We're only going to do a little tiny bit of the mathematics. We're not going to do that much of it. Okay. Oops. Okay. So let me draw a little picture for you just so you can imagine. I find it useful for myself to imagine a gas as like a bunch of particles in a box moving around. So, I've used this sort of image before as we talk about gases. But remember, gas molecules, they're pretty widely spaced. It's not very dense. There's a large number of them, and they're moving. So it's not a bad idea to use little lines, which we call vectors, to describe the direction they're moving. And the longer the vector, the faster it's moving. And so what we find is if you start thinking about these molecules, how fast they're moving. Let's say we did the following experiment. I'm going to put on the x-axis speed. Remember, the other word we use for speed is velocity. And technically, they're not the same thing, but we can use them interchangeably. And let's say that I pick one of these molecules out of the box and study it. I want to see how fast it's moving. And what I do is I plot it on the x-axis, how fast it's moving. And so I'm going to plot it right here. I find out that, hey, that molecule is moving this fast. So I'm going to plot it right here, okay, on the x-axis. So this is faster, and then this way is slower, right? So the further to the right, the faster, the further to the left, slower. So then I do another one. And I'll find out what's interesting is that it's probably not going at the same speed. It could be going faster, could be slower, but on average, it's not going to be the same speed. And then I pick another one. And this one turns out it's going slower. So that kind of makes me interested. I'm like, hey, one's going faster, one's going slower, one's in the middle. What's going on here? So I keep picking them one at a time, over and over, as many as I can. And what you'll find is that some of them will be moving faster and some of them will be moving slower, but there's going to be a tendency for what we call a distribution. Those of you that have taken statistics, you know, you have these things called distributions, binomial distributions, normal distributions, things like that. And this distribution is often what's called a skewed distribution. Left skewed, I guess. And it looks something like this. Ooh, I'm not doing a very good job. There we go. It looks something like that. Actually, let me change the left of it a little bit. I didn't make it very skewed. There we go. There we go. That's more skewed. Okay. It's not a pretty picture. The pictures in your books are better, but it looks something like that. Okay. So that's called a distribution of speeds. Some of them are going faster than other ones are. And what's interesting is that we can actually calculate one spot on this graph, and that is essentially right here. We can calculate this speed. And we call this, it has different names. Sometimes it's called the average speed. Now, the term average is not very technical. I know we use the word average a lot when we deal with numbers, but there's other terms we could use. We could call it the mean speed. Sometimes it's called the root mean square speed, or RMS speed. Root mean square, which is just a way in which it's calculated. That's actually how we'll calculate the speed. And I'm not going to go through all the differences between averages and means and all of that. But essentially, what we're doing is we're saying, hey, if half of the molecules are going slower than this speed and half are going faster than this value, okay, that value we're going to call the mean or the average or the RMS speed, okay? Half are going faster, half are going slower, okay? Which you might actually think it is the median as well. But in any case, it's a measure of how fast they're going. And so I'm going to give you the equation for this. This is called the RMS speed. and it would correspond to this value here. I'm going to put a URMS and a line over it just to give you the notation. It's equal to the square root of 3 times R times T over the molar mass. Okay, so this is called the RMS average speed. And then T is the temperature in Kelvin. Okay, so that's temperature. M is the molar mass of the gas in kilograms per mole. So that's unusual for us. We've been doing molar mass this whole course, and we've always been doing grams per mole, but this equation requires that we use it in kilograms per mole, or have it in kilograms per mole. And then this is the gas constant. And here we're going to use different units as well. We're going to use 8.314 joules per mole Kelvin. And I'm going to make a little, I'm going to box this because this is unusual, right? All the calculations we did with the ideal gas law, we used 0.082057 atmosphere liters per mole Kelvin. What's happening here is we need the units to be in joules, and 1 atmosphere liter is not in joules, but there's a conversion factor. An atmosphere liter is the same thing as 101.3 joules. So what happens is if you take the 0.082057 and you convert it to joules instead of atmosphere liters, you multiply by 101.3 and you get this number 8.314. Okay, so we got to use that 8.314. And the reason is the units. We want the speed to be in meters per second. It doesn't help us to have speed in atmosphere liters or units like that. It doesn't make any real sense to us to have units of how fast something is moving related to atmospheres. So what we do is we say, hey, let's put everything in meters and seconds and kilograms, and all those units will give us a speed of meters per second. So I'm going to box this as well. There's a couple of details about this equation you need to be really careful with. One is the molar mass needs to be in kilograms per mole, and the gas constant needs to be 8.314 joules per mole Kelvin. And then that pretty much will give you the answer. You know, that equation is not that difficult. It's not that complicated. So let me show you. I'm going to write the equation again, but let me show you how we use that equation to do calculations. Okay. So 2 gases are mixed in a container at, I'm going to give it a negative temperature, negative 25 degrees C. The gases are oxygen and helium. Calculate the RMS average speed. And again, sometimes they'll use the word velocity for each gas. Okay. Now, I want to point out something. This corresponds not just to this problem, but to other problems that you do in the chapter. And that is, if you have different gases in the same container, they have to be at the same temperature. They can't be different temperatures. Because if you mix things together, they will collide with each other and then come to the same average speeds. So they got to be at the same temperature. Okay. So in air, for example, the temperature of the nitrogen in the air is the same as the temperature in the oxygen in the air. So let's take a look at this one. So there are two gases. The first one is oxygen, and be careful with oxygen, because for oxygen, remember it's O2, it's one of those diatomics. It's not O, it's O2, and that will affect the molar mass. You want the molar mass in this calculation, so make sure you use O2. So the molar mass of O2 is 2 times 16. So you get 32 grams per mole. Okay. We know the temperature, it's minus 25. I guess I should put a decimal point there because Alex always does that, right? But remember, we need to have the temperature in Kelvin. So I'm going to add 273.15. And so what do we get? 248. 0.15. Okay, so there's our temperature. Remember, temperatures need to be in Kelvin when you're doing gas problems. So there's our temperature. So now let's figure out what the average speed RMS of O2 is. It would be the square root of 3 RT. Remember 8.314? T is 248.15. And then we divide that by the molar mass, but oh boy, this is grams per mole. And we need to have it in kilograms per mole. So here's what I'm going to do. 32 grams per mole, and kilos 1,000. So kilogram over 1,000 grams, okay? The reason we're doing this conversion has to do with the units of that equation. The joule is kilograms meters squared per second squared. So it has kilograms in it, not grams. So for that reason, we have to have the molar mass in kilograms, or we would have to convert R into grams. So, you know, sometimes people will do that as well, but not very often. So that's going to give us 0.03200 grams cancel, kilograms per mole. Okay, so there's our molar mass in kilograms per mole. This is important here. Got to have it done that way. So now we can use the equation 0.03200. I'll go over the units in a moment just to show you. But now we've got all the numbers. So 3 times 8.314 times 248.15 over 0.032. So you get the square root of 193,417, 193,000. So you take the square root of that, and you get 439.79. But let's go back to our sig figs. The molar mass has 4. R has 4 and temperature has 5. So I guess it's 4. So you get 439.8. Okay, so there's your speed, your average speed. So here's what that's telling us. It's telling us that for oxygen, you're going to get this distribution . There we go. Looks something like that. And the average is right here, 439.8 Kelvin. It doesn't give us the whole graph. It only gives us one value of the graph, but that value is an average. So, you know, averages can be pretty useful sometimes It gives us sort of, a measure of, it's a point estimate, I guess is what you call it. It gives us an estimate of how fast these molecules are moving on average, right? Some are going to be moving faster, some are going to be moving slower, but it's a measure of how fast they're moving. Let me show you the units. The units are confused or can be confusing. When we do unit dimensional analysis, essentially you run the units through the same mathematical operations that you do the numbers. So for example, if I say I'm going to take the square root of 4, which is 2, you take the square root of the units too, and you get square root of meters, So you do the same thing here. So let me put the units in. Joules per mole Kelvin, that's R. So that's this number, 8.314. Temperatures in Kelvin. And then molar mass is in, let me make this a little bit bigger, kilograms per mole. So some of the units cancel, right? Kelvin and Kelvin. Moles is in the denominator for both of those, so it counts. So you got rid of some of the units and you get square root of joules over kilograms. So you say, well, wait a minute, what kind of unit of speed is that? I would never say that something is moving at the square root of joule per kilograms. Typically, speed is distance over time, right? So a length over a unit like meters per second or something like that, or inches or miles per hour. But it turns out the issue here, let me erase this. The issue here is, what is a joule? A joule is a kilogram times meters squared divided by seconds squared. So the joule is what's called a derived unit. It has different units in it. So let me put those units in there. We have joules per kilogram. So that's kilogram meters squared per second squared. But then it's divided by kilograms, right? Kilograms. So look what happens. The kilograms cancel. And so now you got the square root of meters squared per second squared. And the square root of something squared is just that something. So the square root of meters squared is meters. And the square root of second squared is seconds. So there you go. And now you got the right units, meters per second. Okay. So careful when you do this calculation. Make sure the temperature is in Kelvin. Make sure the molar mass is in kilograms per mole. And make sure that you're using the value of R that's joules per mole Kelvin. And so if you do those three things, you're going to get a speed that's going to work out to meters per second. And typically those are the units that people are going to want to have the speed in, okay? About 440 meters per second, which is pretty fast. That's around 850 miles an hour, just to put it into perspective. Okay. Okay, questions on that problem for oxygen? I haven't done helium yet. I'm going to do helium next. Okay. Let's do helium. Again, it's minus 25 degrees C. You don't need a lot of information for these problems. You just need the speed. You just need the gas, what kind of gas it is. So you have the molar mass, and you need the temperature. So this is for helium. Again, the overall equation is 3RT over molar mass. Okay. So the temperature, again, we said was 248.15. We figured that out. R is 8.314 joules per mole Kelvin. And now let's do the molar mass. Helium. Helium is element number 2. It's around 20% of the sun. There's a lot of helium in the sun because the sun is converting hydrogen into helium over time. And the sun has about 20% helium. The Earth doesn't have very much helium. So in the United States, we do have access to cheap helium because there are mines in the earth, in the deep mines in the United States that contain helium. But most parts of the world don't have a lot of helium. It's actually it's not that common. So helium has a molar mass of 4.00. Remember, that's in grams per mole. So let's figure out what the molar mass is. 4 grams per mole times 1 kilogram over 1,000 grams. So you get 0.00400 kilograms per mole. Okay, so there's your molar mass. So now we've got everything we need. We went through the dimensional analysis before, so we don't need to go through all that again. Just put the numbers in at this stage. 3 times 8.314 times 248.15 over 0.00400. Okay. So 3 times 8.314 times 248.15 divided by 0.004, and you get the square root. It's big. 1,547,339. Big number, but you got to take the square root. That'll make it smaller. And you get 1243. I think there's only 3 sig figs here in the molar mass, so I'm going to round it to 1240. And again, the units for meters per second. So let me make a little table here. So this is the speed. It's the average speed. This is the molar mass. And this is the gas. Take a look at those numbers. I know it's just 2 gases, but the pattern generally holds. Oxygen is heavier than helium. It weighs more. It goes slower on average than helium. Okay, so in other words, the heavier a gas is, the slower on average its molecules move. The lighter a gas is, on average, it moves faster. And it turns out this has an effect on our atmosphere, because what happens is helium is so light with a molar mass of 4 grams per mole that when it's released into the atmosphere, the molecules move so quickly that they're able to escape the Earth's gravitational pull. And so when you release a helium balloon into the atmosphere, and it goes up, 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 and then eventually the balloon pops, those helium atoms over time will move away from the Earth and actually leave the gravitational pull of the Earth and move out into space. Okay. Oxygen, on the other hand, is much heavier, 32 grams per mole. So those molecules don't move as quickly. So what will happen with oxygen is they're not moving fast enough to overcome the gravitational pull of the Earth. So oxygen tends to stay in the atmosphere, and we don't lose oxygen. We don't radiate oxygen off into space. Okay. So same is true for hydrogen. Hydrogen, H2, it has a molar mass of 2.02. Okay, so this one's going to move even faster. I'll just do a quick little calculation. 3 times 8.314 times 248.15 over 0.00202. Hydrogen, on average, these molecules move even faster than helium. 1,750 meters per second on average. So that's really fast. So same thing with hydrogen. They move so quickly that if those atoms, if those molecules get up to the upper atmosphere, they're actually light enough. They're moving fast enough they can escape the gravitational pull of the Earth, escape velocity. Okay. So the relationship here is that the lighter a molecule is, a gas molecule. And when we say lighter, we mean molar mass. The faster it moves on average. I have to say on average because some of them are moving slower, some of them are moving faster, but on average, they move faster. The heavier a gas molecule is, the slower it moves on average. Okay. In fact, there are some problems where what we were interested in is how much faster does the lighter molecule move than the heavier one. So I'm going to give you a little equation for this. This is called Graham's law. And there are problems in your homework where you have to do this. The average speed of one gas over the average speed of the other is equal to the square root of the molar mass of the second one over the molar mass of the first one. This is called Graham's law. So we can do that for these two gases. I'm going to take these molar masses and we're going to do it for helium and oxygen. So let me show you an example. The average speed of helium divided by the average speed of oxygen. What's their average speeds relative to each other? You take the molar mass of the one that's on the bottom, which is O2. Sorry, it's not easy to see that. O2 is 32. Okay, so it's the opposite of the ratio. So whatever you have on this side over here, it's the opposite on this side. Whatever is on the bottom here is on the top here. Divided by the molar mass of, I'm sorry, oxygen and then helium. There we go. Okay. So now you take the square root of that, you get 8. It's 2.8. So what that tells us is that on average, helium molecules move 2.83 times faster than oxygen molecules. It's kind of cool. It's a very simple equation. I didn't need to do any conversions. I didn't need to convert it to kilograms per mole or use R or use the temperature. What this shows is that the heavier something is, the slower it moves. So helium is lighter, so it moves faster. Oxygen is heavier, it moves slower. And this allows you to calculate how much faster the lighter one moves than the slower one. Okay, the only thing you have to do is just be careful. The lighter one I put on the top, the heavier one I put on the bottom. I don't have to do it that way, but I wanted to do it that way just to show you. When you do that, the heavier molar mass is going to be on the top and the lighter molar mass is going to be in the bottom. This equation, Graham's law, it comes from this equation here. It's not really a new equation. It's just this equation right here that's been manipulated a little bit. Okay. So that should allow you to do any of the problems where they ask, how much faster is this gas moving than that gas? You can use Graham's law for that. Alternatively, you could use this equation for each gas and then take the ratio. So if you take the ratio of 1240 and divide that by 440, you'll also get 2.83. You get the same answer. But this is simpler. Graham's law is simpler. All you need are the molar masses. Okay. Any questions on that one? They're not that hard. The calculations aren't really that hard. You just have to, you know, get the details. You have to make sure the units are right. But for Graham's law, it's really simple because you don't even have to worry about units. Just calculate molar masses, take the ratio, take the square root, and you're set. Okay. Now, there's one more relationship in that equation that we should look at, just so that you can see. And that is the temperature, right? The temperature is important. So let me do this following. Let me take helium gas at, let's do minus 200 degrees C and 200 degrees C. Calculate how much faster the helium at 200 degrees C moves relative to the helium at minus 200 degrees C, okay? So I'm going to do two separate calculations. I'm going to calculate the speed of helium at negative 200 and then at 200 and then take the ratio, okay? So let's try the negative 200 first. Remember, you got to have it in Kelvin, so add 273.15, and that'll give you 73.15 Kelvin. The molar mass of helium, 4 grams per mole. But remember, when we're using this equation up here, you got to have it in kilograms per mole. So you get 0.00400 kilograms per mole. And then just remember, you got to use the 8.314. Okay. If you got that set, you're okay. You'll be fine. So let's do that. Square root 3 times 8.314 times 73.15. Divide that by our 0.00400. Okay, so let's see what we get. 3 times 8.314 times 73.15 over 0.004. You get the square root of 456,127. The square root of that is equal to 675 meters per second. Okay, so there's our average speed at negative 200 degrees. That's really cold. And they're still moving 675 meters per second on average. Some are even going faster than that because that's just the average. So that's around 1,300 miles per hour. Very, very fast. But now let's do 200 degrees C. Now we're doing 200. I didn't do that conversion yet, right? So if the temperature equals 200, you got to add 273.15. You get 473.15. Divide that by the molar mass. And let's see what we get here. 3 times 8.314 times 473.15 over 0.004. You get the square root of 2950327. That's a big number. 2,950,000. Square root of that is 1720. Okay, a lot faster, right? 1,700 meters per second. By the way, that's around 3,500 miles per hour. If you could fly that fast in a plane, you could cross the United States in about 45 minutes. That's pretty fast. So now let's do the question was, how much faster does the helium at 200 move relative to the helium at negative 200? So relative means division. If someone says relative to, they mean do a ratio, A over B. Okay, so let's take the faster one, 1720. Divide by the smaller one, 675. And you get about 2.5. So that means the faster, I'm sorry, let's not use the word faster, let's use hotter. The 200 degrees C helium gas moves 2.54 times faster than the negative 200 degrees C helium gas. Okay, that's a big difference. 2.5 times faster on average. Okay, so if you were to draw a little graph, speed, what you'd find is that you get a graph that looks like this. Oops. So here's your minus 200 degrees C, and then this would be your 200 degrees C. So you see how the 200 degrees C, it's moved over, it's shifted over to the right. It's shifted over to faster speeds. So as the gas heats up, as it gets hotter, the molecules will move faster at that higher temperature. Okay. Any questions about that particular calculation? Okay. Let me just show you one. We have time, I think, for one Alex problem. So let me show you a specific Alex problem. And so here's the one I'm going to show you, which is we want to look at how molecular speeds scale with temperature and molar mass.
Oh, that's the one I was going to ask, actually. I was looking for it. Thank you.
Oh, good. I'm glad. Okay, so we want to rank them. You want to rank their speeds. And 1 is the slowest. And then 4 is the fastest. Okay, so we have 2.7 moles of helium at 3.0 atm and negative 16 degrees C. We have 2.9 moles of xenon at 1.2 atm and negative 16 degrees C. And then we've got 1.7 moles of argon at 1.6 atm and negative 16 degrees C. And then you've got 1.8 moles of xenon at 1.7 atm and negative 33 degrees C. Okay. All right, so notice that they give you a bunch of numbers in here, right? You got moles, the number of moles, you got the gas, you got the atmospheres, and you got the temperature. They're giving you a lot of numbers in there. It turns out there's only 2 that are important, though, because the average speed is the square root of 3RT over molar mass, right? You just need the temperature and the molar mass. You don't need to know what the pressure is or the volume, for example, if they gave you the volume, okay? And you don't need to know the number of moles. Nowhere in there is the number of moles. So here's what you can do. You can calculate for each one of them, just use this equation right here and get a number, and then that'll give you what the rankings are. So let's just, you know, to be honest with you, I don't remember the molar mass of xenon. Xenon is 131.3. So what I'm going to do is I'm going to make a little table here. So let's do it this way. Let's do the gas. So we have helium, xenon, argon, and xenon, right? So those are the four that we're looking at. And then let's do molar mass. Okay. So helium, we know that it's 4.00. But if we want to have it in kilograms per mole, it would be 0.0040, right? You just divide it by 1,000. So I'm just going to move the decimal point 3 places. And then our temperature in Celsius is -16, but we really need it in Kelvin, right? So we're going to add 273.15. So you get 57.15. Am I right? 57, 67, 73. There you go. So I just added 273. And now we can just calculate the speed for that one. Okay. Xenon is 131.3. So if you move it over 3 places, you get 0.1313. This one's also at -16. So that's going to be the same temperature. Argon is in between. It's 39.95. So if you move it 3 places, you get 0.03995. This one's also at -16. So again, that's 257.15. So 3 of them are at the same temperature, so you don't have to do a lot of conversions of temperature, just one of them. And then the last one, the xenon, again, that's xenon. So xenon's 131.3. 0.1313. But this one's at -33. So that's colder, right? Colder is slower. My guess would be this is going to be the slowest one because it's the heaviest and it's the coldest. But -33 plus 273.15 is what? 240, yeah. 240.15. Okay. Now, what I'm going to do is I'm just going to go ahead and calculate. We'll do it for the first one. There's only one time where we're doing helium. So that would be the square root of 3 times 8.314 times 257.15 over 0.00400. Okay. So 3 times 8.314 times 257.15 over 0.004. Don't forget to take the square root. You get 1266. So we can put that up here. That one's going to be the fastest. It really is, because if you think about it, even though those are all negative temperatures, -16 is the hottest temperature in there. It's the hottest. The only other ones are -33. And helium's the lightest. So it's going to be the fastest. You can tell that one pretty easily. Let's do the xenon now. The xenon is the square root of 3 times 8.314 times 257.15. Divide that by 0.1313. So 3 times 8.314 times 257.15 over 0.1313. Take the square root, and you get 221. So that's a lot slower. We know it's not going to be the fastest. The third one is the argon. So square root of 3 times 8.314 times 257.15. And then we're going to divide that by argon, which is 0.03995. So 3 times 8.314 times 257.15 over 0.03995. Take the square root, you get 400. Okay, and then like I said, the xenon's going to be the slowest, this last one, because it's the heaviest and it's the coldest. It's at a lower temperature, so it's going to move slower than the other xenon. So this one's 240.15. It's not a big difference between the other xenon, but it's a little bit slower. So 3 times 8.314 times 240.15 divided by 0.1313. Take the square root, and you get 213. Okay, so what they said to do was to do the slowest is ranked as 1. So let's do our rank. So the slowest one would be this one here, right? The heaviest and coldest is going to be the slowest. The next one would be the heaviest, but a little warmer, right? That's a little faster because it's a little warmer. It's not a big difference, right? On average, they're pretty much moving the same speed. That difference in temperature didn't make a big difference because you're really only changing it by 17 Kelvin. That's not a big difference. And then the third one is going to be the one that's hotter, but in between weights. It's not quite as heavy as helium, but it's lighter than xenon. So it's going to be faster than xenon. And then the one that's lightest and at the highest temperature is going to go the fastest. So helium will be the fastest. Okay. So you can be, if you just consider the molar mass and the temperature, you could get the rankings right, but I would, be careful, particularly, if you have the time, go through the calculations just to make sure, because sometimes when you do the reasoning, you might make a mistake on it. But you could try it both ways and see if you get the same thing each time, and then you're set. Because technically, this problem doesn't ask you to do the calculation. It just asks you to rank them. And so there's a couple different ways you can do that. But me, if when I'm doing stuff and I want to make sure I get the right answer, I try to crank it out, to where I'm certain of it so that I don't make a reasoning mistake. And then I go back and figure that out. Okay.
Professor, I saw this formula, square root of 8RT divided by PM. Is it something different, or we can use it here too?
It's related.
Okay.
Now your textbook doesn't use that one. What is it? Is it this?
It was square root 8RT.
8RT or 8KT?
8RT.
Over
PM.
P molar mass?
Mm-hmm.
And that's equal to what, velocity?
Yes.
Okay, so pressure is force over area. So that would be the square root of 8 times, let's put it in units. Kilogram meter squared per second squared, that's joules. And then you've got Kelvin. I'm not going to worry about the Kelvin, I guess. And then over here you've got kilogram meter per second squared meter squared. And then I won't worry about the molar mass either. Well, actually, the molar mass is. So
because for one of the exercises,
so where did you see that equation?
I just knew about this this formula, and for one of the exercises, I actually used this formula, and Alex showed me that it was correct. The answer was correct. That's why I was just.
Because I'm looking.
I mean, it's more complicated. I'm not going to use it
because I'm looking at the units, because there seems to be, because this is kilogram meter per second squared over meter squared. So the meter.
No, P is not the pressure. P is
density.
Yes.
Mm-hmm. Oh, it's really rho. This is called rho. It's really it's like an R. Okay. Oh, okay. So really what you have is joules per kmol times Kelvin over, I guess this is probably kilograms per meter cubed times kilograms per mole. And then you got the square root of that, right? So let's see. This has got kilograms, so the kilograms are going to cancel there. So you got kilogram meter squared per second squared. So you got your kilograms are going to cancel there. 2 of those meters. Huh. That seems odd. Okay, I'll have to check on that. I mean, if it worked, it worked. The units don't seem to work out looking at it.
Yeah, I just wanted to make sure, but obviously for our formula is much easier.
No, it's fine. If it works, you can use it. You know, there's, like I said, the thing about the kinetic molecular theory of gases is that there's a lot of different Newtonian calculations. So you can relate all kinds of units to it. So if it works, it's perfectly fine. But
Okay.
I'll take a look
Thank
at
you.
it. Thanks for bringing that up. I'd never seen that equation before. Awesome. All right, so I'll put this recording online, and reach out to me if you have any questions this week, the end of the week or this weekend. And good luck with everything in your studying and everything in life, okay?
Thank you.
All right, you guys, take care. Have a great weekend.
Have a good day.
Thank you, you too.